So today we're continuing with related rates, and I have another example for us. There is a car chase. The police car is approaching a right-angled intersection from the north. Okay, so it's coming from the north to the right-angled intersection. And you have to bear with my drawings here. And the police car is going 60 miles per hour. Okay. So I'm just going to write 60 right now. I'm not going to label just yet what it is. But I am going to right now write negative 60. Because even though we talk about speed being 60 miles per hour, when we write a rate, when we talk about derivatives, the positive or negative depends on the direction that it's going. So if we're talking about left, right being positive, left being negative. If we're talking about it mathematically in words, increasing is positive, decreasing is negative. If we're talking about up and down, up is positive, but if you're going down, it's negative. Okay, so if it says it's coming from the north, that means it's going to the south, so it's going down, and it would be negative. So now the next sentence says the speeding car is 0.8 miles to the east. So that's where our car is, and it's 0.8 miles to the east. So since you're going towards the east, you're going to the right, and you're measuring that out to be 0.8. So I'm labeling that as X since that's along my horizontal. And it says when the police car is 0.6 miles north. So that means that I'm going to label the Y, because that's the vertical, as 0.6. The distance between them, since they are moving, it would change, is increasing. So it tells you it's positive 20 miles per hour. Okay. So when I say distance, usually we use S to indicate that. So instead of labeling C like A squared plus B squared is C squared, I'm just going to use an S instead. And so this could be ds over dt because it is a rate, it's in miles per hour. We want to know the speed of the car. Okay? So when we do talk about speed, if we did get a negative answer, we need to take the absolute value of it. Okay? Because that does need to be positive. But in this particular problem, it should work out that we do get a positive answer. So I just want to go back to that negative 60 here. We want to label that as dy over dt. Okay, because that's in relationship to the vertical, which is a y equals. Okay, and when they ask about how, what is the speed of the car, that's asking about dx over dt. So what we're going to do for this problem, instead of like SOHCAHTOA, we're going to use the Pythagorean theorem. So we have x squared plus y squared is equal to s squared. Okay, and we're going to use this actually twice. You'll see why. All right, I'm going to do option 2 here for this problem, where I'm going to take the derivative on both sides of the equation with respect to t. Because as you see in our diagram, we have a dx over dt to find. We're given information about the dy over dt. And we have a ds over dt as well. The only thing missing is s. But by Pythagorean theorem, we can also solve for s. So that's why I said we're going to use this equation twice. One to differentiate, and the other to find what s is. So when you do 0.36 plus 0.64, you get 1. So s, our side is 1. So now we're going to plug all our information into our differentiable function. X was 0.8. You can look at your diagram. dx over dt is what we're trying to find. If you want, you can isolate that first. You don't have to. Y is 0.6. dy over dt is negative 60. S we just found to be 1, and ds over dt was 20. Okay, so when we look over here, we get 1.6 dx over dt. Okay, if you look over here, it's negative 72. So if I add that over here, I get 112. Okay, so if I carefully divide both sides by 1.6, I get 70. So this is 70 miles per hour. Don't forget, we want to say at the moment, or at that moment, the car's speed is 70 miles per hour. Again, speed is positive, so we don't have to say that it's increasing. So we just have to remember to write like at that moment to put it in relationship to this particular scenario. So one more. Example 2, water runs into a conical tank at a rate of 7 cubic feet per minute. The tank stands point down and has a height of 10 feet. And a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? So you may be wondering what's going on here, but luckily they're in different colors if you can see them. So the given radius and height is of the whole conical tank, and we use this to kind of create a proportion so we can solve for R, unless you already see it. So 5 to R is 10 to H for wherever the water level is in our tank. So when you solve for R, we get that it's 1/2 its height. Okay, the radius obviously is 1/2 the height. So if the height is 6, okay, you don't have to find the radius. But what we do need to do is write the volume of our cone as a function of our height. Remember, we always substitute at the ends, like after we take the derivative. So remember, we have to differentiate. So this is unlike other problems where you have many variables to kind of take the derivative, because we don't have many rates to find, we just have this one. Okay? So if you remember option 1, dh over dt, where we're trying to figure out, okay, what it is that we have here, maybe like a d theta, so that way we can do this rule. There isn't anything else. This isn't here. So it must be just to find dh over dt. Okay? So again, keep that in mind. It's pretty straightforward as long as you have a function of h, the height of the tank or the depth of the tank. So the tank volume is 1/3 pi r squared h, and this is not a function. But if I substitute that r is 1/2 h, now we can figure out how fast the water level is rising. So this is more of like a modeling and optimization problem, but it is a rate, so it's really a rate problem. So that's why we have to focus on, understanding all these lessons one after the other. And ask questions if you don't understand something. So dv over dt, okay, is going to be 1/12 pi. Actually, let me write the function. What I was doing is I was writing the function first. So that's 1/12 pi h cubed. So when we find dv over dt, we're getting 1/4 pi h squared dh over dt. Okay. So now, at this point, we'll take into account the whole 9 cubic feet per minute. This is your dv over dt. There's really no way to kind of label that in our diagram. So it's just something we need to substitute when you have the appropriate time. That's a 4, by the way. I know it looks like a 7. H was 6. And this is going to help us find dh over dt. So that's going to be 9 pi, so it's going to be 1 over pi, that is dh over dt. So at that moment, the water level is rising because we got a positive answer at 1 over pi, and this should be in feet per minute. Okay. And if you had a calculator, this comes out to approximately 0.318, but that's just a side note. Okay, you didn't need the calculator for this one. Good luck.